we're going to talk about improper integrals. This is when the upper limit of the integral is positive infinity, or the lower limit goes all the way down to negative infinity. Let's assume we have a function f that is continuous on an interval that is unbounded from above, specifically from a real number a to positive infinity. If we pick any real number b that is greater than a, the function f is going to be continuous on the closed interval ab as well. This means we can take the Riemann integral of f over this interval ab. Now, if f has an antiderivative, this Riemann integral is just a definite integral. To keep things simple, we will just treat it as a definite integral. From there, we let b go to positive infinity. The limit of this kind of integral is what we call an improper integral, which you can see in the very last line. Let's say this limit is equal to L. This kind of improper integral, which we get by taking the limit of a definite integral, can be written as the equation on the second line. What this means is that we are integrating a continuous function f all the way from a to positive infinity. If the limit of this definite integral converges to L, then we say the improper integral converges, and its value is simply L. On the other hand, if the limit diverges, we say the improper integral diverges. By the same token, let's assume the function f is continuous on an interval that is unbounded from below, meaning from negative infinity to a real number b. If we pick any real number that is less than b, the function f will also be continuous on the closed interval ab. This allows us to take the definite integral of f over this closed interval ab. This time, we let it go to negative infinity, which, as you can see in the very last line, gives us another form of improper integral. If the limit of this definite integral converges to L, then we say this improper integral converges, and its value is simply L. On the other hand, if the limit of the definite integral diverges, we say that the improper integral diverges. In this example, we're going to calculate the improper integral of e to the negative 2x from 0 to positive infinity. What this means is that we first compute the definite integral of e to the negative 2x from 0 to b, and then take the limit as b goes to infinity, just like you see in the first equation on the screen. Once we integrate from 0 to b, we get the expression in the second line. Finally, by taking the limit as b goes to positive infinity, we get the value of the improper integral, which is shown right here on the last line. In this example, we're going to integrate 1 over x from 1 to positive infinity. First, we rewrite it as the limit of a definite integral, which is shown in the first line on the screen. Once we compute the definite integral, we let b go to positive infinity, and that gives us the value of improper integral, as listed on the very last line. In this example, we're going to compute the improper integral of cosine pi x from negative infinity to 1. First, we rewrite it as the limit of a definite integral, like you see in the first line on the screen. Once we calculate the definite integral, we let it go to negative infinity, as shown in the fourth line. Now, as it goes to negative infinity, sine pi is undefined because it keeps oscillating. This means that the limit does not exist, and therefore, this improper integral is divergent. This screen shows how we can tell if an improper integral converges or diverges. For some improper integrals, we actually cannot calculate their corresponding definite integrals analytically, which means that we cannot just take a limit to find the answer. For example, if a function f does not have an antiderivative, we are dealing with the limit of a Riemann integral rather than a definite integral. In other words, we cannot use the fundamental theorem of calculus to solve it. When this happens, we can use numerical integration to get an approximation. But before we jump into numerical methods, we can use other approaches to figure out whether the improper integral converges or diverges first. If we can show that the improper integral diverges, the problem is solved right there. We don't even need to bother with numerical integration. That is why learning how to test for convergence or divergence is so important. Let's assume we have two non-negative functions f and g that are continuous on an unbounded interval from a to positive infinity, and f of x is always less than or equal to g of x. This gives us two scenarios. First, if the improper integral of the larger function g converges, then the integral of the smaller function f has to converge too. Second, if the improper integral of the smaller function f diverges, then the integral of the larger function g must also diverge. This approach of testing for convergence or divergence is what we call the comparison test. Of course, this method relies on a rigorous mathematical proof, but we're going to skip that for now. In this example, we want to prove that the improper integral on the screen is convergent. Because we cannot actually calculate the exact value of this improper integral, we can only show that it converges. Here is the explanation why. The fourth line on the screen shows an indefinite integral. The catch here is that we cannot actually solve this integral using any of the methods we have learned so far. But even so, we should not naively jump to the conclusion that this indefinite integral does not exist. It is very possible that the function has an incredibly complex antiderivative, and we just don't have the tools to find it. If we wanted to strictly prove that this indefinite integral does not exist, we have to use a proof by contradiction, basically, assuming the antiderivative exists and showing that it leads to a contradiction. Of course, doing that is really tough and honestly not necessary. Since we cannot calculate the indefinite integral right now, the next best option is numerical integration. And for that, we first need to make sure this improper integral actually converges. Next, we're going to use the comparison test we talked about earlier to check if this improper integral converges. If you look at the second line on the screen, we have a larger function 1 over x to the 3 over 2, and its corresponding improper integral converges, as shown in the fourth line. Now, integrating this larger function 1 over x to the 3 over 2 is pretty straightforward, so we won't go through all the steps here. Actually, you can calculate its exact value directly, but for our purposes, we only need to know that it converges. Since the integral of this larger function converges, the comparison test tells us that the original improper integral has to converge too. One important thing to keep in mind here: when you use the comparison test, the two functions you are comparing f and g must share the exact same limits of integration. In this example, we want to prove that the improper integral on the screen is divergent. Whenever we tackle an improper integral, the very first move should be checking for convergence or divergence. The only exception is if, at first glance, we can easily solve the indefinite integral and use limits to tell if it converges. But usually, finding that indefinite integral right from the start is pretty tough. What this example shows is that, even without finding the indefinite integral, we can still use the comparison test to prove that this improper integral diverges. If you look at the second line on the screen, we have a smaller function 1 over 1 plus x, and its corresponding improper integral is divergent, as shown in the fourth line. Now, the indefinite integral of this smaller function is simply the natural log of 1 plus x. So, it is pretty clear that the improper integral of this smaller function diverges. By the comparison test, the original function's improper integral must diverge as well. This means we don't even have to bother calculating its indefinite integral. Next, let's assume the function f is continuous on the entire real line. The improper integral we want to look at now is shown in the second line on the screen. What we have to do here is split this integral into two parts, one integrating from -infinity to 0, and the other from 0 to +infinity. If both of these separate integrals converge, then the improper integral of f over the entire real line converges as well, which you can see in the second to last line. This screen shows that if the improper integral from negative infinity to 0 equals L, and the one from 0 to positive infinity equals m, then the improper integral of f over the entire real line is just L plus m. In this example, we're going to calculate the improper integral shown in the second line on the screen. First, let's find its indefinite integral, which you can see in the very last line. Using u substitution, we can easily find the indefinite integral, just like the equation shown on the screen. We will start by calculating the improper integral from negative infinity to 0. First, let's rewrite it as the limit of a definite integral, just like the first line on the screen. Once we compute the definite integral, we let it go to negative infinity, and that gives us the value of the improper integral, which you can see on the last line. Next, we will compute the improper integral from 0 to positive infinity. First, we rewrite it as the limit of a definite integral, which is shown in the first line on the screen. Once we calculate the definite integral, we let b go to positive infinity, and that gives us the value of the improper integral, as you can see on the last line. Lastly, by adding the values of both improper integrals together, we get the final value of the improper integral from negative infinity to positive infinity.